we learned some basic things about ensembles. Now the expectation value of an observable O, which is represented by the operator O hat, in pure state, if we measure this observable O, then its expectation value will look like this. And psi, in terms of the component wave functions, that is psi I and psi k, are written like this. And this term can be broken like this, because when we measure in the pure state, this term corresponds to the diagonal elements in the matrix, which are for I equal to k, and this is the interference term where the different states on superposition interfere with each other, and this is non-diagonal terms, and the whole thing will give me the expectation value of this observable in pure state or in pure ensemble. Now for mixed state, we define the expectation value like this, and there is no interference terms. Okay, so now let's go into the measurement of spin half particles, measurement of spins of a spin half particle. Now these are the spin matrices. We have already learned this. We have already actually learned about sigma x, sigma y, sigma z, which are Pauli matrices, and I have derived those matrices. Now if we measure spin in the z direction, that is the value of Sz, which means eigenstate of this Sz operator are 1 by 1 0 and 0 1, and this is up state in the z direction. This is spin down state in the z direction. This state correspond to eigenvalue h cross by 2. This state correspond to eigenvalue minus h cross by 2. So if we measure expectation value of Sz in 1 0, I will get h cross by 2. And if we measure expectation value of the z component of the spin here in 0 1, I will get minus h cross by 2. And the eigenstates of the spin matrix along x direction Sx are like this. This is again for upward direction, this is again for downward direction, and these are the corresponding eigenvalues. Now I will consider this state, this 1 root 2 1 1, that is spin up state in the x direction, and then I will find out the spin value in x direction and in z direction both. That is, I will find out the expectation value of sigma x and I will find out the expectation value of sigma z. Now let us consider this eigenstate of Sx. This I am taking just as an example. This is a pure state, of course, because this is the eigenstate of Sx. There is no mixture of states, as we can see here. Now my job is to find out the expectation value of Sz and Sx both in this state. Now our intuition says that as this is eigenstate of Sx, so I will not be able to get the spin value along z direction if I measure the spin value in a state which correspond to x direction. So let us find out the spin value along z direction. This is my spin matrix. This is the state. This 1 by root 2 is because of this. So if I do the simple calculation, simple matrix calculation, we can readily see that Sz is equal to 0. I mean the expectation value of Sz is equal to 0, and that's quite obvious. Now let's find out the expectation value of Sx in its own eigenstate, and as it is a state which corresponds to upward direction of spin, so I must get h cross by 2 plus h cross by 2, and I have calculated that. So the physics is okay. I mean it's going well with the mathematical calculation. Now we need to measure Sz. What happens if we try to measure Sz in this eigenstate, in this particular pure state? Because of the measurement, this system will collapse into eigenstates of this spin z, I mean this Sz operator, which means this state is now a mixture of these pure states, because I'm trying to measure the value of Sz in this state. So this is the eigenstate of Sx, and now it is written in terms of the eigenstates of Sz, which is the effect of measurement. So after I try to measure the Sz in this state, the wave function becomes this and this. This is having a probability, this one, because it's AI mod square, as we have just learned and we know already. And this state would appear with a probability of half. So here I'm going to find out the expectation value of Sz in the mixture of these states. So let us calculate. We have calculated the expectation value of Sz in a state which I obtained after I try to measure the value of Sz, and I have found that it is 0, and it should be. Now before I got the value 0, now if I try to measure the value of Sx in psi after, then I am getting 0 here. Now this is quite surprising, because when I tried to measure the expectation value of Sx in its own eigenstate, which is a pure one, and which is this one by root 2 1 1, I got h cross by 2. But now the state is looking like this. So these states are the eigenstates of Sz operator, so it will not be able to give me the expectation value of Sx, and that's what I have found here.